Aloha, this is RBrewer with the Hawaii Department of Health. This is the recording of a presentation I gave to the U.S. EPA Incremental Sampling Methodology Technical Committee on April 21st, 2021. I've added some slides, some additional notes on questions that came up during that presentation, included in this presentation and this recording. The title of this presentation is G's Theory of Sampling and the Hawaii Department of Health Critique of the 2020 ITRC ISM Update. Some of my colleagues and I have been discussing the dilemma of collecting samples for soil. Someone pointed out that in the 1970s, a group of astrophysicists and engineers built a machine the size of a small car called the Voyager 1 spacecraft, launched it into space. After 3 billion miles traveling through space, they had it turn around and take a picture of the Earth. See in this picture by Carl Sagan, named the pale blue dot of the Earth. So think about all the technical difficulties and logistics behind doing something like this, and perhaps sampling soil is so hard. We've been trying to think about in more detail why are we having so much trouble doing something as seemingly simple as collecting a sample of dirt. So we'll discuss that during this presentation. So the references: in 2016, we published our technical guidance manual, which discusses what we refer to as decision unit and multi-increment sample investigation methods. 2020 ITRC posted an update of their 2012 document on incremental sampling methodology. And then later on that year, our office again published a critique of the use of the ITRC incremental sampling methodology guidance for use in Hawaii. In reality, as I'll discuss later, we got a lot of comments and input from consultants and regulators on the mainland who are familiar with our guidance and also with ITRC. It's more of a joint effort. And at the bottom, you can see the URL for our web page on DU-MIS investigation methods. It includes information on research that our office has carried out and other links and guidance we've published, as well as a lot of recorded webinars. Our guidance manual discusses DU-MIS sampling, what I like to refer to as risk-based site characterization, in sections 3, 4, and 5. You can see here how they're laid out. Systematic planning, developing a sampling plan. And section 4 discusses how to collect samples in the field. Section 5 gives a lot more details on actual field work. And updates to this guidance are pending. We should have some posted sometime this summer. It's also a 6-part DU-MIS training webinar series that we posted in 2017 on our YouTube webpage. First, I want to give a quick background of decision unit multi-increment sample investigation methods here in Hawaii. We actually started in 2014, so 17 years ago. Between then and 2008, we started carrying out a lot of field studies, initially agricultural land, as we were faced with redevelopment of really large areas of abandoned sugarcane fields here in Hawaii for residential development. We started off with training by Chuck Ramsey with Envirostat. It's highly recommended. If you haven't heard of him, get in touch. Also, we initiated our internal Department of Health field team. We spend half the year, one person does in our office, looking for abandoned sites and gathering background information. The other half of the year, then we go out and actually collect samples ourselves. This has been a huge benefit for our office in understanding how to do field work, what works, what doesn't. We also published draft guidance during that time. 2009 and 2015, we first published our formal DU-MIS guidance in 2009. Also started expanding our experience at industrial sites, which we'll discuss. And then we carried out a detailed field study of discrete sample data reliability in 2015. We published a paper on it in 2017. In 2016, based on experience we gained, we updated our DU-MIS guidance. By then, just a wild guess, we'd collected over 15,000 multi-increment samples here in Hawaii. So the laboratory chemists told me once that they were testing around 2,000 samples a year. By then, we'd been doing this for over 10 years. 2018, I actually met with Francis Pittard and a group of international sampling statisticians in the mining industry. And this is where G's theory of sampling and the whole idea of decision unit multi-increment sample investigation methods and ISM were developed. And that was really beneficial for me, understanding what they were doing in the field and how they had developed this method. So we'll discuss that later on in the presentation. And here in 2021, the second update of our guidance is underway, and hopefully we'll have it published sometime this summer. My friends and I, who spent the early parts of our career collecting discrete samples, basically putting random handfuls of dirt in jars and having laboratories test random pinches and spoonfuls of that. We always like to joke about how we went through the 5 stages of sampling grief as we started to understand more about testing of soils and other particulate matter and the errors that's just inherent with discrete samples. So we all go through this anger, denial, bargaining, depression, acceptance. And it's a standard process of science and learning in general. It's actually a lot of fun once you get to the acceptance part anyway. We've been involved with ITRC's ISM document from the beginning. In 2010, 2012, we actually assisted in preparation of the proposal for the initial guidance with ITRC. I attended one of the first meetings they had, was unable to attend the rest of the meetings for various reasons, and mainly provided outside technical support for preparation of that document. We knew when it was published there were some problems with it, and certainly some parts we disagreed with. We still disagree with it. Showed up in the update. In 2018, 2020, I and William Harmon with the Michigan Department of Environmental Quality actually prepared the proposal outline for update of the 2012 ISM document. We commented on drafts of the document, but again, I was unable to directly participate. At that time, I was moving back and forth between here and China, working with the Chinese Academy of Sciences on preparation of similar guidance for that country. William Harmon attended the first part of the preparation of the guidance. He actually got frustrated at some parts and for various other reasons decided to leave. He wasn't involved in the final document. So for the critique of the 2020 update, I want to break it into 2 parts. Part 1 is the introduction discussions and discussions of field and laboratory implementation. And part 2, statistical concepts, data evaluation, and use of ISM type data in risk assessments. So we provided comments on each of these sections during preparation of the document, and we got no response from ITRC, unfortunately. Input, again, I mentioned before, input for the critique that we published in November 2020 is provided by multiple consultants and state and federal regulators experienced in DUMIS and ISM. It's not really just a Hawaii critique, it's more group-wide effort. I start with the introduction, field and laboratory implementation. This was really well done overall. There's really good discussions on the unreliability of discrete sample data throughout these sections and implementation of ISM, as they refer to it, in the field and the lab. Don't really have a lot of comments on this. I'm going to go over some of the background of the unreliability of discrete sample data, just the introduction to the issues about risk, using discrete sample data to assess risk. That section was really missing in the document. A few things, comments we had was, one was the term sampling unit throughout the document. In our opinion and our experience, an unnecessary term, and this really led to some poor planning and unreliable sampling in the field here in Hawaii when consultants from the mainland have come over who have read the ISM document. There was an idea that you could take a standard decision like an exposure area or something and split it up into smaller units, what they were calling sampling units. You didn't really collect like a 10 increment sample in each one and try to determine the extent of contamination using those type of data, which would be unreliable from the beginning. Also, we'll discuss that in more detail. Also, the document recommends a default 30 increment samples for testing sites in general. This was actually in our early guidance. At that time, we were only testing agricultural fields. And since then, once we moved on to industrial sites, we realized, and the consultants here did, you really have to bump up to 50 plus increments per sample to get good precision. None of this stuff, as Morpheus points out here in the bottom, is a surprise. When I started doing this type of work back in the 1990s, and was collecting samples in the field, it was always a question, what if I move my sample point over a foot? Would I get the same number? What if the lab tested a different pinch or spoonful of soil from the jar, even if they tried to stir it with a spoon or something? would they get a different number? We assumed there would be a problem with that, but we never knew how to quantify it, and we didn't really have an alternative. And both when I was a consultant and a regulator, the regulators were accepting it anyway. So we just kept moving on from site to site. Let's start with our discrete sample data reliable. I call this part one. It's the reliability of data for single samples for site characterization. It was never tested or demonstrated in the field. Several people on the call know Dina Crumling, formerly with the EPA Superfund office at EPA headquarters. She spent a lot of time looking through old EPA documents and passing them on to me for use in the paper that we published. We're trying to figure out where this idea of testing discrete samples came from. No other intensive or sampling intensive industry in a similar type of media, in the mining industry, agriculture, would ever collect discrete samples and send it in. Here's some key assumptions that we dug up at some of the early EPA guidance. First, from 1985, where they first proposed a use of discrete sampling methods and grids. The level of the contaminant is assumed to be uniform within a contaminated area and zero outside of it. And followed up in 1989, when there's little distance between points, it is expected that there will be little variability between points. If you read the details of these documents, it seemed like the authors knew this may not be correct in the field. They were basically saying, hey, these are the assumptions we're making if you want to use this discrete sampling method. We don't know if it's right or not, but here's the assumptions you need to keep in mind. Really, what they'd had most experience with at that time was discharges of wastewater from industrial treatment plants. This is basically the group of people that wrote the early guidance for testing soils. And unless the process inside of plant changes, then any kind of discrete sample from the wastewater pipe would be very similar to any other sample. So it's fairly uniform within that wastewater. And if you collected a sample at different time periods, then the sample's data should be very different. They were thinking of this for soil, it's probably similar because a lot of it was contaminated with liquid contaminants. It's kind of like spilling paint on the ground. It's either there or it's not. So you have a uniform concentration within and it's zero without, with sharp boundaries. So just some of the assumptions went into the early guidance. And this all led into the use of discrete sample data for risk assessments also. We carried out a field study starting in 2015, published it in 2017. Went out to 3 sites known to be contaminated. Each site we designated 24 grid points, and around each grid point we collected 5 discrete samples. We had them processed properly using ISM type methods and independently tested. We took 1 sample unprocessed and had it tested 10 times. We looked at the variability, total variability between co-located discrete samples. With the arsenic site that we investigated, this was associated with discharges probably of arsenic contaminated wastewater. Average total variability between discrete samples about 2-fold. This would shock most people in the field, I think. You're trying to estimate the extent of contamination, and the potential error in your data uncertainty is 2-fold. That was actually the best site we had. At the lead contaminated site, this was lead contaminated incinerator ash mixed with fill material. There, the average total variability within a sample and between co-located samples is about 7-fold. At this particular site for lead, Hawaii's screening level for lead residential use, it just happens to be 200 parts per million. Pretty much at every single grid point site, a grid point at that site, we could find a discrete sample with less than or greater than 200 ppm. Just imagine all the confusion that would cause in the field trying to characterize the site. The PCB site, the PCBs have always been a nightmare trying to characterize in the field. Average total variability between discrete samples is about 39-fold. This is the photo of the worst sample we had, where one sample at the lowest at this particular site was 4.9 ppm, highest just a few inches away, 2400 ppm. Now the variability you see here between samples, these may seem pretty high levels in ppm. We saw the same variability in lower concentration samples. So it wasn't really concentration dependent. We also saw the same variability within a single sample as we were seeing in the co-located samples around a single point. This is all due to distributional and compositional heterogeneity. It's referred to in G's theory of sampling as a source of discrete sample variability. Some of the lessons learned here at this for the PCB site, these nuggets of PCB infused tar balls, they may not be included in a subsample. So in one sample, you may get a few ppm. You test another sample, you get hundreds of ppm. So if you think about it, this is, again, gets to risk. There's always been this thought of maximum contaminant concentration in soil. But the concentration is completely dependent on the scale that you test the sample. If you test a large mass of soil, say the entire sample on the right, you might get a few ppm of PCBs. If you test one of these single PCB infused tar balls, these nuggets, you'd probably get hundreds of ppm PCBs. Again, that would have been in the same sample you collected. If you could zoom in with some type of microscope or some kind of detector on the matrix within one of these tar balls and zoom into a single patch of PCBs, and ultimately you'd get 1 million parts per million PCBs. So the maximum concentration of a contaminant in soil is a key point. The key kind of realization we had is either 1%, it's either 0% if it's absent, if it's not in the soil, or it's 100% if it is there. Anything in between, you're just diluting it with soil. So the key point here is the concentration varies with the volume of the mass of soil tested by the laboratory. You're going to get a different number if you test the lab tests 1 gram of soil from a sample you send in versus if they test 30 grams, a 30-gram subsample of soil. So this, a key point with respect to risk is that individual discrete sample points do not represent exposure points. This is something I really messed up in the early parts of my career. And the concentration from a risk standpoint, my background's in geology, so I do the site investigation, also in risk assessment, so I assess risk. But the concentration in default 100 to 200 milligrams a day soil ingested, say by a child or an adult, is not represented by this discrete sample data that you're collecting in the field. So another key point, it's a huge problem for using discrete sample data. Risk-based screening levels are never intended for comparison to discrete sample data. The risk assessment objective in these risk-based screening levels only apply to the targeted area that is decision unit mean. So keep those points in mind. We'll discuss use of discrete samples in risk assessment. What's the primary cause of failed confirmation samples? They really did a good job discussing this in the ITRC's ISM update. Or worst case, something you'd never want to hear happen if you're a consultant or you paid for the investigation, discovery of new contamination after cleanup. So key points, the lab data for discrete samples are not reliably representative of the sample provided to the lab. They don't process the sample properly or test large enough mass most of the time. And the sample submitted to the lab is not reliably representative of the area where it was collected. So at best, for characterization, use of discrete samples are highly inefficient and wasteful at best. And I can definitely say that from a lot of personal experience collecting discrete samples. So you can't, the problem with this whole approach in terms of characterization is there's no clear endpoint in sight. It could just lead to repeated investigations, the confirmation samples fail and such. You can't fix this problem by collecting more and more discrete samples. You just dig yourself deeper into the hole. Eventually you run out of money and walk away. Hope you got it right. Your problem can't be fixed by statistical evaluation of discrete sample data, and we'll talk about later. And a lot of detailed studies on this issue were carried out by the U.S. Army Corps since the 1990s at munition sites. Again, it's nothing new. We just need a way to address it. And again, the ITRC ISM update does a good job of addressing and explaining these problems. Now, one issue we had with the document was the continued use of this idea of sampling unit. And from our reading of the document and discussion with people that wrote these sections, you could replace the term sampling unit with decision unit in pretty much all cases. They define a sampling unit as the smallest volume of soil for which a concentration value will be obtained no matter the intended purpose of the data. So that when we see something like no matter the intended purpose of the data, where there has to be some purpose, that's one issue. And then it also says it's commonly used to support a specific decision, such as a risk-based decision for a known exposure or a source area. So some type of decision is always going to be made on the sample data you collect. And most uses in the ISM document reflect the definition of a source area or a boundary DU. So there's really no reason to have another term like sampling unit. So misuse of the term, as I mentioned before, is encourage sloppy sampling in the field and decision making based on unreliable data. There's inadequate number of increments are collected, what people are referring to as sampling units, was just a sampling unit. Or inadequate sample mass, poor sample collection methods, and then premature conclusion that one area is more contaminated than another. And this, it's common, we see this in reports, oh, this was just for screening. Anytime you see that, it should throw up a red flag. That pretty much means that decision statements for how the data are going to be used once you get it back haven't really been thought out adequately. Just an example of sampling units. This was actually one of the questions and issues we discussed most in my presentation to the EPA's ISM committee, was the just use of the term sampling committee or sampling unit. So let's assume this is an exposure area. It could be acres in size or your backyard or something. Now, if normally you would just test the entire exposure area as 1D, you could collect one sample or maybe collect triplicates, so you test the precision. Let's say you suspect a spill area in one part of this exposure area decision unit. An exposure area DU is typically the largest you'd ever want to make a decision unit. Well, you suspect that it's contaminated in one area, so you don't want to collect a sample up front. It'll probably fail. It'd be more efficient to isolate that area and test it separately. One way you might do this is split the suspected spill area into multiple smaller source area decision units. How many decision units you split it into, 1 or 4 or 10 or whatever. In part, it depends on the type of contaminant present and the cost of the remediation. So it's more of a cost-benefit analysis on how many DUs you want to split this into. Once you've done that, then you would designate boundary DUs around it just to confirm that you've caught the contaminated area adequately. So again, in this example here, there's no need for the concept of sampling units, but in a lot of examples they give in the ITRC ISM update discuss these exact type of sites. Also in the ITRC ISM update, another definition they're referring to as sampling unit. One type of atypical unit involves a series of small areas, sometimes only a square feet, sampled to gather information about contaminant spatial patterns or concentration trends. What they're really referring to here is we prefer to call just good discrete samples. But instead of grabbing a single random handful of dirt from a point, then within a few square foot area, collect a 1 to 2 kilogram mass sample. So you have a good sample mass and collect it from multiple points within there. And then ideally you'd process the sample before you test it. So we actually include the guidance on this approach in our technical guidance manual in section 4.3, use of discrete samples. We use it sometime at sites. It's normally only time and cost beneficial if you can screen the samples in the field. So we'll go out to a site and collect samples and bring them back to someone, stationed somewhere with an XRF, and let them shoot them while we're bringing continual samples to them. Or you could shoot it in situ in the ground. It's just for screening in that point. And the only decision you're making is how to split the site up into decision units for more detailed DUMIS or ISM type sampling. So those aren't really sampling units either. Call those discrete samples. It keeps it more clear, I think. One thing that came up during the presentation was, what about large areas where we use this example in our guidance for testing of very large agricultural areas. In this case, this example was a 400-acre field. It's a real example. There's a pesticide mixing area in one part of it. So we isolated it to test it separately. They wanted to put houses on the rest of the field. So it'd be around, if we assume a default 1 acre lot size there would be 400 lots. And each lot would represent an exposure area. So 400 exposure area decision units. Well, the way this works in our guidance in Hawaii and the way the developers have been doing this, first, if they just want to screen a large field like this, they would do a baseline investigation where they split the field up into, could be very large, tens or even hundreds of acre DUs. DUs for testing based on the crop history, pesticide use, soil type, topography, development plans, etc. There's no set number. And then they collect a single multi-increment sample on each one of these DUs and look at large-scale buildup of pesticides. And at that point, they may walk away if they find stuff, or otherwise they may decide to move on to a more detailed investigation. They will collect triplicates in 10% of the DUs just to test overall precision. If they want a letter from our office concurring that the land can be redeveloped, then they have to start thinking about these hundreds of exposure area DUs within the field. It becomes impractical to test all 400 of these, so another option that we have in our guidance is to test 59 randomly tested or randomly selected 1 acre DUs for testing, then collect triplicates in 10% of these DUs. In this case, all 59 of these DUs must pass the screening level for it in order to have a 95% confidence that 95% of the DUs in the total area would pass. Now, during the presentation EPA, we discussed, could we refer to these 59 areas as sampling units? Because really, in part, you're making a decision on the whole field. Do I want to take this field and redevelop it for residential housing? And during the presentation, I was thinking, well, maybe you could refer to these as sampling units, but when you think about it in more detail, there actually are exposure area decision units. It's not really a good use of the term sampling units. You're just only testing a partial number of these exposure area DUs, more for cost limitations. So sampling units don't really fit in there either. So where do they fit in? Not really sure. We have specific guidance on investigating former ag fields, really large. How many of these default 1 acre exposure areas you really need to test when you need to do a baseline investigation? This is all in our guidance. So this is a figure I think would have been useful for the ITRC update, and we'll put it in our next update of our guidance document for DUMIS. So there we recognize 3 different types of decision units. One is risk-based DUs, like exposure area decision units. That's the most common. We think about it, at least in terms of risk assessment. And remedial optimization DUs, where you know you have contamination, you want to isolate the contamination to optimize the cost and efficiency of remediation. And here, ITRC document breaks this down into source area DUs, where you think it's going to be high concentration, and boundary DUs, where you think the concentration is going to be below screening levels. And then you have other types of DUs. One thing we have in our guidance, we refer to it exploratory borehole DUs, where you're making a call on a single borehole. That's usually on the extent of contamination or just the nature of contamination of site-specific contaminants. You're not really making risk-based decisions or final decisions for remediation. So, where do sampling units fit into this? Really, I still don't know. And all the examples that are given in an ITRC document would fit into this scheme here. So that's one thing we recommend, is avoiding the term sampling units. Some of the risk-related key points then that are tied to characterization using discrete samples. So the first key point is the objective is always the mean of the exposure area concentration. Or if you're looking at risk-based or source area DUs and such, you always want the mean concentration. So risk-based screening levels are never intended for comparison to individual discrete sample data points. Then a key point here, moving into risk assessment, data for a single discrete samples for a single discrete sample does not represent the hypothetical exposure point concentration, or the concentration of the contaminant in the assumed 100-200 kilogram mass of soil that an adult or a child would ingest over a single day under risk assessment exposure assumptions. So the data for discrete samples do not directly reflect variability in exposure point concentrations within an exposure area. That's a very common misunderstanding between field samplers and risk assessors. Let's look at the second part of our critique then. This dealt with the statistical concepts, computer simulations, and risk assessment. So again, with the field work, the discussion of discrete sample data unreliability, laboratory processing, we thought that was really well done. But in these sections, we definitely start having problems if you've read our critique, the details of it. The things missing from the ISM update here. First was a summary of the statistical basis of G's theory of sampling. There's decades of field research that I was hoping someone who was working on the document would be able to go through. We haven't had time to do that. That would have been very useful where they're collecting samples the mining industry has in the field and looking at different variables and parameters that relate to error in your sample data representatives. This would have been much more useful than these simplistic computer simulations that are included in the document. Computer simulations, they're okay to start with just for a general screening level. All they tell you is the more points you collect, the better the more reliable estimate of the mean you have. Not a big surprise. But the problem is these sections relied on those computer simulations way too heavily and completely overlooked the other points of error in G's theory of sampling. Another key thing that was missing from the update, discussion of the hidden and unknowable error in a 95% UCL calculated for a single set of discrete samples. We'll look at that in more detail. Also related to this, the distinction between the variability within a single set of discrete samples. That variability reflects compositional and distributional heterogeneity of the contaminant in the soil within the targeted DU, compared to variability between replicate ISM samples. They reflect the overall sampling method precision, so they're completely unrelated. Also missing from the ISM update, this was really critical. It was the distinction between a 95% UCL for a single set of discrete samples and a 95% UCL for multiple ISM samples, which is completely unrelated. This is one of the biggest lapses or flaws in the ISM update. And the problem with this is that the people who wrote this section more or less inferred, or essentially were requiring that replicate samples be collected in every single decision unit within an area, within an investigation, so you could calculate a 95% UCL, because that's what EPA guidance recommends. And sure, risk assessors would feel more confident with a 95% UCL in some cases. We'll discuss that some. But EPA's guidance on use of a 95% UCL was completely based on the use of discrete sample data, recognizing the high variability in those data and difficulty in estimating a reliable mean contaminant concentration. Again, we included all these types of comments to the draft of the document. We never got any response to it. We also offered to put the team writing these sections in touch with experienced sampling statisticians in the mining industry, which I'll point out later goes through the exact same process as the environmental industry. This is our discrete sample data reliable part 2. To key point, the reproducibility of the mean based on a single set of discrete sample data is not routinely tested with replicate samples. That's a huge problem. And just like the use of discrete samples to characterize the extent of contamination at site, it's never been demonstrated in the field to be reliable. With the use of a single set of discrete sample data to estimate the mean concentration of a contaminant within a targeted decision unit has never been tested in the field and demonstrated to be reliable in terms of following your traditional discrete sampling methods. Dina Crumling and I again dug through some of the older EPA documents trying to find out the basis of this. One, in risk assessment, you often hear the idea that you should collect at least 20 to 30 samples in order to estimate a reliable mean. Well, this is the quote this comes from. It's a 1992 supplement guidance to risk assessment guidance from EPA. So sampling data from Superfund sites has shown that data sets with 20 to 30 samples provide fairly consistent estimates of the mean, i.e. there is a small difference between the sample mean and the 95% UCL. Well, that's not the way you demonstrate consistency in a single set. Consistency, it requires comparison to replicate sets of data. You go back and do the same thing, collect another 20 or 30 samples at a site, or are you going to get the same number, yes or no? So we couldn't find the database that was used to come up to support this statement. And we haven't seen any data comparing replicate sets of discrete sample data estimates of the mean to support this statement. In the Pro UCL User's Guide, collecting 20 to 30 samples within every area within a site exposure area gets really expensive if you're doing discrete sampling methods. It's rarely done. In my experience as a consultant and as a regulator, I would say 99.9% of cases, you're not going to get 20 to 30 samples to attempt to estimate a mean from. And again, as we discussed, you wouldn't really know if it's accurate anyway. So in the Pro UCL guidance, it basically said, well, at least try to collect 10. So you've reduced the reliability or the certainty of the data even more. At least 10, then you can run your statistical models on the data. I know the author of the Pro UCL guidance, and I talked to her. Her husband also wrote it about it, and they say, well, Roger, we do what we can. These consultants, basically the geologists, I would say the field people like me, they give us a table of data and tell us to make sense of it. And here's what we can do with that data. They can't. It's the quote here from another statistician. The statistical analysis of the data only evaluates the precision of the statistical test employed to estimate a mean for the data set provided. It doesn't tell you at all if the data set provided was representative, or how much potential error could be in it. And that's that you always see this in any risk assessment, is that one of the limitations and uncertainties section of the risk assessment is that the risk assessors are assuming the data are representative. Well, the mining industry went through the same problem, from time beginning up through the 1950s. And as we'll discuss, they're the ones that worked this out first because they had to. So in the mining industry, I went to the Independence mine just north of Anchorage, Alaska. It's great if you ever go up there and you like this kind of stuff, start looking at their signs. They were thinking about the same thing, even in the late 1800s, early 1900s. Here's one poster on sorting ore increases profits. Well, that's DU designation. They're separating their source areas from their non-source areas so they can isolate the highly contaminated stuff that's full of gold or something. And then if you go over to their assay office, here's another poster. They're doing the similar type of sample processing and data analysis. They had their top statisticians involved. Here they're grinding the samples. At least they knew that up front, and testing them. But then the problem is then that the mining companies are going to sell their ore to some extraction company. The extraction company is going to crush it up and melt it or do whatever and extract the commodity. And until the 1950s, what they extracted almost never matched what was estimated based on the sample data collected. So you always have unreliable estimates based on statistical analysis of the discrete sample or the composite sample data. So when you underestimate your mean, as a company, you're giving away your commodity, which isn't good for your company. If you overestimate your mean, then you're cheating your customer and you're not going to get that customer back anymore. If you have really poor data precision, so you test it and get one answer, maybe the company that's going to extract it, they test it and they get another answer, or at some point the customers aren't going to trust you. So it was a huge problem in the mining industry for centuries in reality. Ultimately, what was realized was that poor sampling methods most commonly underestimate the true mean or the true mass of the commodity in the ore. So that was a big incentive to come up with a better way to collect samples. And they knew right away it's not a problem with statistics, it's a problem with how the samples are collected in the field. So by the 1950s, there's been a lot of research done before this time, and a guy named G in France started compiling all of the research that had been done and some of his own thoughts and notes on how to collect more representative samples of particulate matter, in this case like crushed ore. And this was his theory of sampling of particulate matter. And the bottom line here is you collect a large sample from a large number of points. That's really all it came down to. Here's an outline of Francis Pittard's book in 2019. I've also got his 1993 book, which it's a great book too if you want to read it. His 2019 book is more of a collection of papers by a lot of sampling statisticians around the world. You can see the different sections of it. So the main point in his book and in the research they're doing is that error in the estimation of the mean concentration and commodity or contaminant mass is related to the collection of the sample. Again, not to the statistical test employed. So leave the statisticians alone for a minute and get your people in the field trained so they can collect more representative samples. The solution was pretty simple. First, you crush the ore. You want to get into small particles. It's practical. Then you're going to collect a large mass of material from a large number of points. They refer to as increments. This is what's referred to in our guidance by Chuck Ramsey, trademarked the term as a multi-increment sample. Just on the side, they never used the term incremental sampling. G wrote his notes. He never wrote a book in French, and Pittard in his 1993 book calls it increment sampling. And then the number 3, the last thing is carefully process and subsample the process sample for testing. Then you get a reasonable mean and reasonable estimation of mass. So there's a ton of research available. Again, it was too bad we didn't see this in the ITRC update. And we try to put them in contact. In reality, a lot of people on the team just don't have time, just like we do, to compile all this information. This is a photo from a 2018 World Conference on Sampling and Blending. It's in Beijing, China. I just happened to be there. Actually, I was one of the first environmental people ever to present at the conference. They don't like the environmental industry, to be honest, because of this whole discrete sampling silliness. But they're coming around now. Next conference is going to be in Norway in 2022. Anyone interested to really understand how to collect samples of particulate matter like soil, sediment, or crushed ore, that's the place to be. From left, I list the main people there from left to right. These are all just top-notch sampling statisticians with the mining industry. Francis Pittard is the third from the left. So look for books and papers by these guys. A lot of women. It's a huge mix. Hundreds of people at this meeting from all over the world to get an idea of the depth of research that's been done. Right? And you can also just look at his book. So again, we try to put some of the ITRC risk assessors and sampling statisticians in touch with these folks, but they didn't have time, and I think they didn't really understand the importance of it. This is why miners figured it out first. It's all about economics, and most problems in the world all comes down to money, and also in third-party verification. So in the mining industry, they have the crushed ore, and it's sampled to estimate the mean commodity concentration in mass, and then they're going to sell this crushed ore to an extraction company. The extraction company wants to know, if I buy 20,000 tons of this ore, it's kind of a typical unit, I think, how many grams or of gold am I going to get out of it, or kilograms of iron or whatever commodity. Now, in the mining industry and extraction industry, they want a data precision for replicate samples of 5%, even 1 to 5%. So imagine that. You have to get your concentration term right within plus or minus 5%. Well, how do you do this? It's not collect a lot of samples. You're still going to collect one sample, but it's going to be huge. And some of the folks I talked to in Beijing typically collect 1 ton plus multi-increment samples from say a 20,000 ton stockpile. And then they'll crush it, subsample it, and they'll actually melt their subsamples and crush that and test it. And they claim, and they can do it, they can get down to 1 to 5% precision on their replicate sample data. So that's pretty amazing. They call it grade, we call it risk. There's a lot of competition to get as accurate a sample data as you can. That's what's driven it to so much depth in the mining industry versus in the environmental industry, to get the number right, because it's third-party verification, and whoever can get the most consistent and most reliable sample data, they win, and they get to sell their ore. That's why the environmental industry is still struggling. First, there's no replicate data in terms of the risk assessment. What's replicate data in the environmental industry? When I was a geologist collecting samples, where you collect 2 side-by-side discrete samples, you take the highest number. Well, that's not really replicate data. Definitely when you're using discrete sample data to assess risk, no one goes out and collects multiple individual sets of discrete samples and calculates means from those to compare and to test the precision. So that's the problem with the environmental industry. We weren't required to test replicate data. And people like me now, the consultants at the time, regulators were accepting it, so why bother? There's very little third-party verification. No one really goes out and extracts all the PCBs or lead in the soil or arsenic to determine the mass and then test to see how accurate your data were. Only time we get an idea of really the depth of error in discrete sample data is for in situ remediation. And I've talked to a lot of people and done some myself, in situ remediation, especially for VOCs. And the people doing this already realize and accept up front that the discrete sample data are going to underestimate the mass there, and they typically over-engineer the project by at least 10-fold to ensure that they cover the mass that's actually present at the site. So that's why we had problems in the environmental industry. I want to step back for a minute now with the sampling theory basics. It's a really good set of a pair of documents written by the Association of American Feed Control Officials. So, so why am I talking about feed control? Well, here it's all about testing grains. There's two documents, or types of particulate matter. There's one called Good Samples on how to collect samples in the field, and then the second is on Good Test Portions on how to test samples in the laboratory. And it's completely what you would refer to as ISM type sampling methods, or DUMIS type sampling methods. If you want to learn more about this, or just sampling in general for soil or whatever, then again, I'd recommend getting in touch with Chuck Ramsey, taking his 4-day sampling for defensible environmental decisions training course. If you've been doing discrete samples for years and years and prepare to go through the 5 stages of grief, if you haven't, it's still very worthwhile to take, and you won't fall back on the problems that we've had in the past. Now, one really useful thing that they bring up in this document is this idea of finite versus infinite element media. And this really helped me understand the difference in the way you test different types of material. So finite element media are media where the elements are individually identified, randomly selected, and tested. And this is the kind of statistics and such that we learn in high school and college and such, where we want to know information about a room of people, or maybe a forest of trees, or cans of tuna, bags of rice, bags of soil, bottles of water. These are all what this document refers to as finite element media. This contrasts with infinite, what they refer to as infinite element media. In this case, elements cannot be individually identified, randomly selected, and tested. So think of an individual grain of flour or grain of rice. So these types of infinite element media include a pile of flour, a pile of rice, a pile of soil, a lake of water. You can test individual drops, a room of air, or even a subslab vapors underground. These are all infinite element media. So these pose different types of sampling problems. Understanding this is really key to getting the environmental industry on board, collecting better sampling data. So testing of finite element media, this is the easiest media to sample. Common DQOs include variability between elements, it's age, mass, quality, or whatever, estimates of maximum, minimum concentrations, or other quality control parameters, very typical, especially in the food industry. So the sample, again, is prepared by collecting and testing individual elements. The only variable of interest really in statistics, from a statistical standpoint, is the number of elements selected in classical statistics. And this is what the statistical concept sections and risk assessment sections of the ITRC ISM update are referring to, is testing of these finite element media, not really testing of soil. That was the biggest problem with those sections. Versus testing of infinite element media. It's much more complex to sample. Common DQOs here, the most common one is the estimate of the mean of a target decision unit area and volume of the media of interest. So the sample is prepared by collecting and combining groups or increments of individual elements into a single bulk sample for processing and testing. So in this case, variables include the sample mass. That's critical when you're testing infinite element media, sample mass or sample volume. And the number of increments, the number of elements. In this case, it's the number of increments. Yes, that's also very important. Also, you have to look at the collection method. How is the sample actually collected in the field, and how is the sample processed? These are all parts of G's theory of sampling. So this is the type of statistics we need to be thinking about, of concepts and such, when we're testing particulate matter like soil and sediment. This would have been useful to discuss in ITRC update. And I think we provided them the references, but they didn't look at them. So here, let's look at a testing of indoor air as one of these infinite element media. So the risk question, does the mean concentration of contaminant X in the volume of air Y circulating in the room during classes exceed screening level Z? It's just a very basic risk question we'd ask at any site. Well, one way to test the air, you could collect 10 discrete samples. So you take a little syringe around the room and real quickly draw bits of air into it and shoot it into a GC or something and test it. And you can use that to calculate a mean and 95% UCL. But First questions are going to come up. Well, how many samples should I test? What volume should each individual sample be? Should it be 5 milliliters or 100 milliliters? Of course, nobody's going to do this in the indoor air testing industry. And the indoor air folks they've had sampling theory down pat for pretty much forever, for years. So here's how you would do risk-based collection of indoor air samples. Let's just assume you have a room, or this is the default volume of a house, 244 cubic meters, indoor air exchange rate 0.35 times per hour. If I did the math right, over 24 hours, you'd have around 2 million liters of air circulating through that room or through that house. So that's our DU, is these 2 million liters of air going through the house. We only want one number. What's the mean concentration of TC or whatever in that air? Well, ideally, we take that entire DU volume and send it to the lab for testing. And that'd be equal to about a beach ball about 15 meters high. Well, that's a bit too big to send to a laboratory. So in reality, we're going to collect a single sample from the air. We're going to collect a single continuous sample during the targeted exposure duration. Let's say it's a 24-hour sample. That's our exposure time we're concerned about, using a sumicanister or a passive sample or something like that. So then we get the data back. Those data are going to represent 2 million liters of air, even though we may have put it in a 6-liter sumicanister. Now, there are some assumptions behind this. It assumes the air circulating past the collection point is representative of that targeted volume of air as a whole. And from a risk standpoint, you may be assuming that targeted day is representative of long-term mean and such. A lot of assumptions you have to think about. You can collect replicate samples. You can put a sumicanister in another part of the building or another that's being targeted, and then compare that. You can do it on different days and such to test your overall sampling precision. And they do this. So the indoor air people, they know what they're doing. It's us dirt and mud people need help. So the same concept really applies to testing of soil and sediment. So who would have thought of that, right? Testing soil and sediment is actually a lot more similar to testing of indoor air than it is of testing people with classical statistics and such. So we have a very similar type of risk question. Does the mean concentration of contaminant X in the area or volume of soil or sediment Y exceed the screening level or risk Z? And again, we have to start thinking about things like, well, how many samples we're going to test, what mass. In the left, here's a picture of 1 kilogram of soil, just to want an idea of what it looks like. That's our minimum sample mass for multi-increment samples, about 1 million particles if it was 1 millimeter size particles. Here's the laboratory subsamples, PCBs, pHs, or so, 10, 30 grams of soil. It's basically a spoonful. For metals, 0.5 gram to 1 gram. It's just a pinch. Imagine going to your backyard. You're concerned about your kid being exposed to PCBs or lead. How are you going to test it? Well, I'm going to go out and randomly test 10 pinches of soil in my backyard and assume that represents the mean for that whole volume, hundreds of cubic yards of soil as a whole, and base my risk-based decision on that. So it doesn't really make sense. No one in the indoor air industry would surely do that. No one in the mining industry would ever do that either if they're looking for gold. How can you collect risk-based soil and sediment samples? This is what ISM is supposed to address. So let's jump to a front yard, say 400 square feet, depth about 2 inches. It's only about 2.5 cubic yards of soil, not that much, 2,500 kilograms. So we're going to test this. It's considered an exposure area, DU. At first, let's pretend the soil is a flattened stockpile or even a piled up stockpile instead of an exposure area. So we don't get confused about individual points within that, testing individual points within the soil and calling those exposure point concentrations, because they aren't, as we discussed before. So the first thing that would come up was, how should a soil sample be collected? Well, option one, same thing with indoor air, and this is what the mining industry ultimately does, is you excavate and send the entire volume of soil to the lab for testing as a single sample. So you get one number back and use that data to assess risk. That's the best way we could ever do it. And that would represent the true mean of the soil. So there's no sampling error because you didn't collect a sample. You sent the entire population or DU to the laboratory. This isn't done in the environment industry, but again, we get some insight from failed in situ remediation where they are trying to treat entire DU massive soil. And there's always way more contaminant there than was estimated in discrete samples. But this is a hypothetical option. Here's option two, which I did in the first 10 years of my career. Again, I was a geologist and a risk assessor, so I was collecting the samples and then giving them myself to assess the risk. So you could collect 10 plus discrete samples, like it says in the Pro UCL guidance, test each sample individually, and then use some statistical analysis to address variability and estimate a mean. This is what's in past US EPA guidance, including using a 95% UCL. Same questions come up for indoor or whatever is how many samples should I collect? And what should the mass of each sample be? Doesn't that matter? Shouldn't it matter if I just put a pinch in each jar? In reality, the mass of samples has been totally driven by the mass the lab needs to run the analysis. It has nothing to do with risk or really science as far as getting representative samples. So the problems with this traditional discrete sample data method, and they discuss this in the text again, in the ITRC update, is the samples aren't collected or processed in accordance with sampling theory for particulate matter, number of points, sample mass, processing, etc. A key thing in terms of risk assessment is that replicate sets of data are never collected to test the overall sampling method precision. And from my risk assessment experience as a consultant, you're lucky to even get 10 samples period to do a risk assessment. And someone wants you to estimate a mean, just from a cost standpoint in time, and you're never going to get replicate sets to compare that to. Actually, I never thought of it as a risk assessor because it would never happen in the first place. So you get a really false sense of the precision of your data and the accuracy of your data in your future decision making. So there's a lot of hidden error in discrete samples, and this is something that we really wanted to see put into the ITRC update. It was in the outline that William and I put together. You have a section that focuses on this. It's a key point to understand why risk assessors, just like the field people doing site characterization, need to transition from discrete samples to ISM type samples. This goes back to the field study that we did here in Hawaii several years back with the 3 different sites. Each one of these sites, we in essence collected multiple sets of discrete samples and estimated a mean, and then looked at the variability between means between different sets of discrete samples. This is the example using collecting 10 samples per site, per set of discrete samples, and we did it 20 times. So at the arsenic site, that was the lowest variability. With these 20 different samples, we got a range in the mean concentration of 218 to 395 ppm. You can see the 95% UCL, it's going to be a little higher, a little bit wider variability. RSDs, kind of high. It threw up a little bit of concern for a risk assessor. But what are you going to do as a risk assessor? Because chances are they don't have the time or money to go back and collect samples, more samples. You give them an answer. Here's a key thing here. What's the mass of soil represented by that lab data? Because they don't process the samples properly at laboratories and use ISM type methods, then if you're testing metals, that single data point only represents 1 gram of soil, basically a pinch. With that in perspective, if you go to a restaurant, we start going back to restaurants, then a packet of sugar weighs about 2, 3, 4 grams. So you're just testing a pinch. The most that data might represent 10 grams of soil. So each sample point only represents about 10 grams total if you're testing for metals. At the lead site, site B, you see a little bit higher variability between the estimated means based on the random 10 discrete sample data sets, 170 to 356. PCB site, so assume 20 people went out to this site, each one of them collected a set of 10 discrete samples, had them tested, estimated, calculated a mean concentration, 5 to over 1,000 ppm. So think about that from a risk assessment standpoint. Did you get that sample data set that gives you 5 ppm, or did you get it that's 1,000 ppm? It's completely random which data set you get. So this 95% UCL, or the mean calculated from a single set of data, it's going to be random within an unknown range if you're using discrete sample data. And the error, the variability between different sets of data, you see it's errors due to inadequate number of samples and or a total sample mass that's tested. That's why you're seeing a lot of variability between data sets. You would only identify this if you collect multiple or replicate independent sets of discrete sample data, of discrete samples. Of course, that's never done. So the representative of any given data set, discrete sample data set for use in a risk assessment, is unknown. There's some margin of error in there. You're not really sure what it is. That's something we was really hoping that the ITRC group could look into in more detail. Another big problem from the beginning when I started doing risk assessment is tossing the outliers so that you can fix the data variance. That never made sense at all from a field person. Because I collected that sample, I know the PCBs were high in that corner of the yard of lead or such, or the use of the maximum concentration for duplicate samples. That just had no science behind it. So these were early red flags that something was wrong with the way we're doing risk assessments based on discrete sample data. I can guarantee you that if you work for a gold mining company and you tested discrete samples and then you threw out the samples that had really high concentrations of gold, that you wouldn't have a job for very long. Or if you just looked at the maximum concentration. Of course, it's going to be 100% if you zoomed in and tested a small piece of gold in your sample. Now, a lot of the problems we're discussing here with site characterization, risk assessment, people in EPA and other consultants and such, they knew about this in the late 80s, but they lost out in their discussion of the reliability of these approaches were being proposed. This is from the Methods for Evaluating the Attainment of Cleanup Standards 1989. All data not known to be in error should be considered valid. High concentrations are a particular concern for their potential health and environmental impact. Well, that's true in science terms, but it messes up your calculation of UCLs. So just get rid of it. That was the decision that was made. And then Petard has been harassing the environment industry for decades. In this case, I think he was talking about the mining industry too, as a common error has been to reject outliers that cannot be made to fit a statistical model. The tendency has been to make the data fit a preconceived model instead of searching for a more appropriate way to collect samples. So your best option, again, the point of the ITRC document is combine lots of increments of soil into a single large sample, carefully process and analyze it, and collect replicate samples in 10% of the DUs through our guidance to verify overall sampling method precision. And we refer to this again as multi-increment sample. So this, a key point here, and another point that's not brought out in the ITRC update, which is really a major flaw in the document, I have to say, in the risk section, is that this whole approach, following G's theory of sampling, the proper way of collecting samples in the field, it replaces the use of a 95% UCL for a single set of discrete samples. There are two different approaches for estimating a mean for a targeted volume of particulate matter, or soil and exposure area in this case. So that's, they're not comparable in that sense. The sample data have to meet specific collection procedures, minimum increment mass and such. Again, in our experience, you need a default 50 increment sample, 1 to 2 kilograms, processed properly. And then now that when you do this, your data represent a much larger mass of soil than typical discrete sample data set. You're talking about, they represent kilograms of soil instead of a few grams of soil. The concentration of contaminant is directly reported for the DU, so you don't need to do statistical analysis or manipulation of the data. And you test the total sampling precision with replicates. That's what we're trying to get to. So if you compare the discrete versus ISM for risk assessment, this would have been good too to include an ISM update, but it wasn't. And there is some political opinion against saying too many bad things about discrete sample data. We should all admit that, because we spent the last 30 years collecting this type of data and making big decisions on sites. In our experience, just to step back a minute, in most sites, I would say at a third of the sites where we did discrete sample data, we wasted a lot of time and money, or all of them really did, and we cleaned up more than we needed to. And then I would say at a third of the sites, we probably got it pretty much right. We just spent more time and money doing it than we would have if we did ISM or MIS type samples. Then another third of the sites, we probably missed some contamination. How big a risk that is, I'm not really sure. Probably not that much at some, but at some sites, it would be a problem. Just comparing discrete sample data versus ISM type sample data for use in risk assessments. Your discrete sample data is you collect 10 to ideally 30 plus single increment samples. That's all a discrete sample is. It's a single increment sample. Versus ISM type sampling, you collect multi-increment samples composed of 30 to 75 plus increments. And for discrete sample data, the sample mass is, you you collect in the field, it's really just based on laboratory needs. And ISM type methods is based on G's theory of sampling, decades of research in the mining industry. At a minimum, you want 1 to 2 kilograms. They might collect tons of material for their work because they want such a high precision. Discrete sample data is no strict processing required of samples. There is obviously an ISM type sampling. And then a key point, discrete sampling data approaches your 95% UCL is used to estimate the mean for risk assessment. ISM type sampling method, the mean is directly reported. And no replicate samples aren't collected in discrete sampling investigations. They are in ISM type investigations, and they're used to assess the precision of the overall sampling method. They're not used to estimate a 95% UCL, at least that's not the default. It's just an added step that isn't done in discrete sampling investigation methods. So the representatives of individual discrete sample data set, it's always going to be unknown. You're not going to know what the error is unless you collect replicate sets samples. Whereas it's specifically tested in the field for ISM type sampling methods. Minimum number of increments in the ISM update document said 30. I think they got that from our guidance in 2009. So that's what was in the 2012 guidance. And even by 2012, when that document was published by ITRC, we were realizing in the field 30 increments per sample isn't cutting it at a lot of our industrial sites. So this is from our guidance now. If you can assume low DU heterogeneity, typical for aerial fallout or application of water-based spills or something, or pesticides, solvents and such, you can probably get away with 30 increment samples because your compositional heterogeneity and your distributional heterogeneity be lower, especially your distributional. If you have sites contaminated with lead-based paint, lead shot, PCBs, bits of tar and such like that, munitions, you need to get at least 75 increment samples to get a high precision for your replicate samples. So our default is 50, just because most sites fall somewhere in between these two examples. But at PCB sites here in Hawaii and lead-based paint sites, by default, most of these are going to be surface samples too. So you get 75 increments while you're out there. It doesn't take that much time. You can make much more reliable decisions and avoid the need to go back and recollect samples. If that's something you don't want to do as a consultant, is have to go back and collect samples again, especially if it's your own cost. So this 50 increments per sample been demonstrated in Hawaii to be, over the last 15 years, to yield much more reliable replicate sample RSDs. When we first started this in Hawaii and consultants are doing 30 increment samples, it's pretty common to get an RSD, relative standard deviation of your replicate samples, over 35%, maybe even up to 50%, sometimes even above that. Once they bumped it up to 50 increments a sample, they very rarely get RSDs greater than 35%. Another thing in the ITRC update, it says in the risk assessment section, or I think in the computer simulations, that you should do totally random collection of increments in a random pattern, kind of in the bottom left where it says least reliable. This is based totally on the computer simulations. And somebody told me a long time ago, models tell you exactly what you tell them to tell you. That's pretty much what these computer simulations in the ITRC document did. They told them exactly what the people who'd programmed those simulations told them to tell them. But that's not the case at all in the field. It's been demonstrated by the U.S. Army Corps doing their munitions work, and by definitely in the mining industry and such. The most reliable way to collect multi-increment samples, ISM type samples, particulate matter, is a systematic random grid, as we show here in the upper left-hand corner. So don't try doing the totally random grids. Your data precision is going to take off, be much too high in a lot of cases. Another thing you have to watch for in the field, on the bottom right, you see these lines of increments. That's really tempting, especially when you're in a really overgrown site. Just go in one line and collect 10 or 15 increments per line, and then go over 20 feet or something and do another line of increments. But the spacing between the increments isn't the same laterally and vertically. So this is another bad method. If you did replicates, you're going to get bad RSDs, or you could. So this the picture you see here where it says 6 feet. This is from the Maui airport. Next time you go there, this is for social distancing, and these folks know how to collect the increments. You can tell because it's 6 feet in either direction. Doesn't mean line up have lines 6 feet apart, it means everybody has to be 6 feet apart. So think of socially distanced increments. So that was another problem in the ITRC document, the risk section. Moving on to toward the end here, sample data quality and usability checklist in the ITRC document has a very similar checklist to the one that we put together. We actually put together, William Harmon and I did, and provided to ITRC group. Step one is the most important part of even a risk assessment or anything. And then when you do an environmental investigation is check how they collected the samples. So review their site conceptual model and the decision designation. Was that done appropriately? Were the samples appropriately collected in the field? Did they collect core shape samples and proper number of increments and such? The proper sample mass. Were the samples properly processed, subsampled, tested by the laboratory? You need to be testing a minimum 10 grams even for metals at the laboratory. If they didn't do this, you're done. You don't need to worry about replicate precision and 95% UCLs and such because your data aren't representative of the field conditions. They're not reliably representative. That's something a risk assessor totally needs before you hand them a bunch of data. It needs to be representative. So you fail that if you don't pass this step. Step two, then, once that looks okay, then you go on to your replicate data precision. These are the samples from our field study from sites A, B, C, arsenic, lead, and PCB sites. And here at the arsenic site, you see the multi-increment sample replicates 220, 230, 250, really good replicate sample relative standard deviation, 6.5%. Each one of these samples represented 1 to 2 kilograms of soil. So if we took the mean for all three of those samples, we're looking at 5 or so kilograms of soil, pretty directly representative by the laboratory data because they process the samples. Site B, we saw more variability at lead site, so you see the replicate data spread out a little bit more, 240 to 350, still not bad. RSD 20%, and typically we'll talk about in a minute if it's less than 35%, then you're good to go. But site C, the PCB site, and think about this these were discrete samples, a single set discrete samples. 3 samples, 19 ppm, 24 ppm, and 270 ppm. Now, what if you collected the 19 ppm set of discrete samples or something? You would never know how much error we had in this data. And these are multi-increment samples unless you collect replicates. So with our replicate MI samples, we know we have a problem with how we were collecting the samples. In this case, not enough increments, not enough sample mass, very high RSD. So our 50 increment samples worked really well for the arsenic and lead site. They don't for the PCB site. And this is one reason we bumped it up to 75 increments for PCB sites. And for PCB type sites too, and lead and such, you really want to get your DUs small and focused on source areas because that's where you're going to have especially high variability. So you don't have to go back and resample. This PCB site, it's easy call for risk assessors. In this case, our screening level is 1.1 for total PCBs. But think about this resampling for toxic or waste, 50 ppm. We're not really sure what the concentration was in the DUs there, so they had to go back and the consultant went back and retested this entire site. Lots of DUs, I think 75 increment samples and small DUs in order to assess for disposal as toxic or waste. And this is updates to our guidance just posted this week actually next week or two, replicate data precision. A key thing here is when are we as regulators going to force consultants and the private parties who are paying for it to go back out and resample? One of the comments we got from the ITRC ISM presentation we gave on the critique of the ITRC ISM update, the presentation we gave EPA, was that this approach here isn't based on statistics, at least once the RSD exceeds 35%. So, and that's true. There's definitely some subjective calls here in professional judgment. But from our experience and from a risk standpoint, looking at the safety margins that are built into these screening levels, which are easily a factor of 2 or 3, if not 10 or more, and even when the RSD starts to exceed 35%, between there and 50%, we're still confident that the data are good enough. If you think about the mean for all, say, 3 replicate samples, then it's going to be a 90 to 150 point sample. With tested 5 kilograms of soil, that's probably as good as you're ever going to be able to do as far as estimating a mean. Once your RSD gets above 50%, say 50 to 100%, then we would say the data aren't acceptable for final decision making. Either recollect samples, or at least at this point, we're saying adjust the data with respect to the replicate RSD to improve its safety margin. So you're assuming you're kind of setting a hypothetical maximum replicate sample concentration for DUs where you don't have replicate samples collected. And then for a very poor precision RSD greater than 100%, then you got a big problem. So some possible exceptions on when we're not going to make you go back and recollect samples is when the screening levels are clearly exceeded, so you have to do something anyway. Or when the screening levels, when they get low enough, below some factor below your screening level, say a third of the screening level, and if you collected the samples properly and other considerations we'd have to think about, we may not require resampling of the site. But if it's a high-risk site, say it's a playground or something, we probably would. And this comes down to Mr. Aristotle, just paraphrasing him here. It's a key part in the environmental industry is it's the mark of an instructed mind to rest easy with the level of precision that the decision requires, and not try an exactness that is unnecessary for the problem. That's something we want to think about more too in the ITRC update. We didn't in the risk section, but that's something that the risk assessors, we need to get together and think about this more. What kind of precision do we really need to make decisions? It's definitely not as high a precision as the mining industry, plus or minus 5% of being accurate with our data. It's much higher than that. So to summarize now the ITRC ISM document, it's getting a lot closer. Here's a comparison with the mining industry. It's the same process, same steps, just a different objective. So in mining industry, geologic mapping, ore sorting, ore crushing, sample collection, processing, subsampling, and testing. Then a key part, data quality review, where the samples collected properly. What's the precision of your field replicates? What's the laboratory precision? What's your analytical precision? This is all used for them for assessing the ore grade, which is a term they would use instead of risk assessment. They're not going to adjust the data. You take the data as is or you throw it out. And then they're going to extract the commodity. That's their ultimate objective. So it's the same process here in the environmental industry with your conceptual site models, DU designation. No need to crush the samples. We're already dealing with soil. You might grind them in the laboratory as part of the processing. That's another issue. Then you collect the samples, process, subsample, test. That whole part of the ISM update was well done, except for the terms, sampling unit. Of course, we didn't like and bump it up to 50 increments for collection samples. It was a data quality review, essentially. Those sections dealt with statistical concepts and risk assessments and such that really needs more work, more revision. They discuss the sample collection method, that's great. But how you deal with the field replicate precision and laboratory replicate precision and such, and what level of precision do you need to make decisions is really missing from the document, something we need to add. Analytical precision is always going to be good. Analytical precision is rarely a problem in the environmental work. It's always the field work is the problem. And then the risk assessment section for the same issues we discussed, that definitely needs to be revised. And try to think about a distinction between the finite element media and infinite element media in that approach for this section. Then in the end, of course, it's the same objective, similar anyway, contaminant destruction and isolation. So I end with the recommendations. ITRC first post comments on the drafts. We had big discussions with ITRC about this problem. There were other documents over the last 10 years. And they said, we'll post comments on the drafts to the web page for the document. They didn't do that for this ISM update, and they didn't do it for others. And so we would say, withdraw the ISM update for the revisions that we pointed out here, then start coordinating. It will help coordinate discussions with outside sampling statisticians experienced in the mining industry. They're the guys that wrote the guidance, wrote G's sampling theory, and they know how to do this. It'd be a big help. So you get your statisticians and risk assessors and your field people together with these folks. Meet them in Norway. They'll be in Norway in 2022. I definitely plan to be there. US EPA, recommendations for them. It's the year 2021 now, so you need to caution states and EPA staff on continued use of discrete sample data for site characterization and risk assessment. People within EPA have been warning EPA management about this since the 1980s, but they've been kind of ignored. Well, now we're kind of getting a second generation of investigating sites that we did back in the 1990s. They're getting redeveloped for other purposes and finding out that, guess what, a lot of this discrete sample data, we really blew it. We may have wasted a lot of time, money, or hey, we may have missed a lot of stuff. So you should really start recommending collection of ISM type samples for all final decision making. This is what we did in Hawaii the first 2 or 3 years. You could use discrete sample data to design a remedial action plan, but we wanted ISM, or we call it DUMIS data for final decision making. Also recommend focused use of 95% UCLs on ISM replicates for decision making if you have a high exposure DU and there's a minimal safety margin in the screening level. That's one point time when we agree, you may want to use a 95% UCL, but that's the only time. Definitely not for every DU. It's a waste of time, and it goes against the whole idea of the theory of sampling in the first place, just to avoid manipulation of data like this. Recommend collection of replicate sets of discrete sample data to test overall sampling method precision at sites where discrete sample data will be used to assess risk. Some of the folks in EPA and on the ITRC team want to see UCLs, period, for all DUs. Well, do the same. This to test overall sampling precision. We'll do the same thing for discrete sample data. We start requiring replicate sets to test the precision of your discrete sample data. You're going to find a lot of surprises, I bet. And then especially, let's get everybody together and carry out some more expanded field studies of discrete sample data reliability. So with that, we went on to questions with the presentation I gave to EPA. I've covered a lot of them here. That's why this presentation went on a little bit longer than there. Here's a quote I ended with Thomas Paine on the scientific method. And I would apply this definitely to myself. For the first 10 years of my career, I was putting random handfuls of dirt in jars and making decisions on it, and knowing that, like Morpheus said at the beginning, that something's wrong with this approach. And now we know how to fix it. So let's fix it. Thanks.